As we work our way through these examples on the back side in regards to over and under estimates for our sums, let's use our graphing calculator to help us get these graphs going. The first function is e to the x, and we're interested from 1 to 4, and we want to know if we do a right-hand Riemann sum, will this be an under approximation or an over approximation? So I'm going to bring in the calculator, and you can see I actually have all of the functions ready to go, but right now only the e to the x function has been activated. And I'm interested from 1 to 4. So I'm going to go to my window, and I'm going to make the x min 1 and the x max 4, and then I'm going to choose zoom fit. All right, zoom fit happens to be zoom 0. And what that does is it puts the y-axis so that we can see that part of the function. So this is the e to the x function from x equals 1 to x equals 4. And we can see that function is clearly increasing. And we know that if we're talking about an increasing function, again, I'm just going to copy the function real quick right here. All right, and we're doing a right-hand Riemann sum. Well, those rectangles are going to be above the curve, and therefore we are talking about an over approximation. All right, why? Because e to the x is increasing. All right. With number 11, we have 4 minus x squared. I'm going to bring the calculator back in. All right, and I'm going to go to y equals. I'm going to turn off the e to the x and turn on the 4 minus x squared. And we can see that our bounds are from 0 to 2. So I'm going to go to the window and type in 0 and 2 for the x min and the x max. And now I'm going to hit zoom, and again it's option 0. Let me do so. Now it's going to graph that, and we can see that we have a function which is clearly decreasing and concave down. We're being asked to do a trapezoid sum. All right, so we know that when we have a concave down function, a trapezoid sum is going to be an under approximation. All right, so it'll be an under approximation. Why? Because 4 minus x squared is concave down. Number 12, we're doing a left-hand Riemann sum. Excuse me, a right-hand Riemann sum on natural log of x from 1 to 6. So let's turn off our semicircle and turn on the natural log of x. Our window is from 1 to 6. And when we do zoom 0, all right, here's our curve again. We see that it is increasing and it is concave down, but we're doing a right-hand Riemann sum. All right, so it doesn't matter about the concavity. Right, as we make our right rectangles, we can see that once again this is going to be an over approximation, right, because natural log of x is increasing. With number 13, we're looking at a left-hand Riemann sum for the function x cubed, the opposite of x cubed plus 1. So we'll turn that one off and this one on. Our window is from -2 to 0, and zoom 0. Here's our function, which is decreasing. All right, so we have a left-hand Riemann sum. All right, it's actually over here, and it's decreasing. All right, so in the upper left corner of the rectangles, we're going to be touching the curve. We can see once again those rectangles are above the curve. So this is also an over approximation. Why? Because the opposite of x cubed plus 1 is decreasing. Now we get into the tangent lines. We want to write the equation of the line tangent to f of x equals x cubed plus 2 at x equals 1. All right, let's take care of that first. So we know that our equation is y minus y1 equals m times x minus x1. And this right here is our x1 that was given to us. So we know we're going to have x minus 1. We get our y1 by plugging x1 into the original function. So we're interested in f of 1. F of 1 will be 1 cubed plus 2, or 3. So we have y minus 3. And then we want the slope. We want the slope of the tangent to the curve at a point. We know that means the derivative. So what's our derivative? Derivative of x cubed plus 2 is just going to be 3x squared. We're interested in the derivative's value at our x1, which is 1. So we want f prime of 1. So that's 3 times 1, so that is also equal to 3. So we have this right here. We have y minus 3 equals 3 times x minus 1. Okay, and we want to use this equation to approximate f of 1.1. That means we're going to plug 1.1 in for x. So we know that basically we can add 3 to both sides, so y is equal to 3 times x minus 1 plus 3. And y is f of x, so f of x is 3 times x minus 1 plus 3. We want f of 1.1 to be approximated, so f of 1.1 is going to be 3 times 1.1, oops, sorry about that, minus 1 plus 3. 1.1 minus 1 is a tenth, so we have 3 times a tenth. We're going to add 3 to that. 3 times a tenth is 3 tenths. So we are looking at approximately 3.3. Now the question is this an under approximation or an over approximation? Well, let's go back to our graph. We're going to turn off the previous problem, turn on the next one, and we're interested around the point when x is equal to 1. So I'm going to go to my window, and I'm going to go from 0 to 2. That puts 1 right in the middle of it. And, oops, and I got to, actually, let's do zoom 0. And we can see that our curve is definitely concave up. So if our curve is concave up, I'm going to draw it real quick right here. Okay, then we know that what we're dealing with is a tangent line which is below the function. So this is an under approximation. Right? Why? Because x cubed plus 2 is concave up. All right, and finally we have g of x is equal to the opposite of e to the x. And we're going to do the same thing that we did in problem number 14. And this one's going to be a little weirder just because we've got the e to the x going on here. But y minus y1 is equal to m times x minus x1. And we know that x1 is equal to 2, so we're going to have x minus 2. And we have, to figure out the y1 value, the y1 value is going to be the function's value at 2. So that will be negative e squared. So we have y minus negative e squared. And you can write that as y plus e squared. And then we need our slope. Well, first we need our derivative. So we need to find g prime of x. And g prime of x, we see the negative sign. That's a coefficient of negative 1. So it's going to go right into our denominator. And then we have the derivative of e to the x. And the derivative of e to the x is e to the x. We're interested in the derivative's value at x1, which is 2. So we're going to plug in 2, and we're going to get the exact same value of the opposite of e squared. So this right here, as weird as it looks, is actually the equation of line tangent to the curve. Right, we want to know if this is an under approximation or an over approximation. All right, well, and we're interested specifically at x equals 2. And I know we have to approximate g of 1.9. So again, we're going to plug 1.9 in for x right there. So y would be equal to negative e squared 1.9 minus 2. And then we have to subtract e squared from that to move this e squared over to the other side. So that's a pretty messy decimal right there, and you can use your calculator to figure it out. But more importantly, under approximation or over approximation. So we're going to go back to the calculator one final time, and too far. And we're going to turn on the opposite of e to the x, and we're interested when x is equal to 2. So we're going to have our window go, let's just say it goes from 0 to 4. That puts 2 right in the middle. So 0. And here's the opposite of e to the x. We can clearly see that this function is concave down. And because the function is concave down, all right, what we are looking at is a tangent line which is over or above the curve. So this is going to be an over approximation, and the reason why is because the opposite of e to the x is concave down. So hopefully this set of examples has helped to give you a better idea of what we're looking for when we're trying to determine whether a sum or a tangent line is an over approximation or an under approximation.